Hello and welcome back to Chemistry from Jay's House. To finish off the year, we're going to have a series of videos that are just going to review all the topics that we covered throughout the year. So we're going to start with the atoms and the periodic table, the foundations of chemistry. So an atom, as you hopefully know by now, is real small. And when we talk about atoms, we spend a lot of times either talking about their nucleus or talking about their electrons. So if we look inside the nucleus of an atom, and that's that center portion, it's always drawn as a circle, but really what it should be is just a collection of like balls stuck together. But it's easier to see it inside of a circle. That inside there are going to be two things, two tiny bits. So an atom is the whole collection, it's everything in the nucleus and all the electrons. That is considered one atom, but it's made up of the smaller bits. One thing it is made up of is these guys, which are protons. Protons just because they're positively charged, so we call them protons. I don't know, we'll put 8 of them in there. Okay, so there we go. We have 8 protons, and then also in there are things that have no charge. So I'm going to write an N to mean no charge. They are neutral. And they get the name neutron because they're neutral. How many is that? 2, 4, 6, 7, 8. Now this particular atom that I'm drawing right now has 8 protons and 8 neutrons. That's the kind of classic. In fact, it even has a name. It has a name, oxygen. And that big 8 there in the side merely tells you how many protons there are. So I'm going to move this over, and I'm just going to leave it there, and hopefully we'll see that it has 8 protons. So any atom that we see walking down the street, regardless of the neutrons, regardless of what's happening outside with the electrons, if it has 8 protons, it gets the fun name oxygen. So there we go. Now, there is, most of them have 8 and 8. Most oxygen atoms have 8 and 8. And if we just do quick math, 8 neutrons plus 8 protons gives us, hopefully everyone's screaming 16 atomic mass units, right? So it weighs 18 atomic mass units because each proton weighs 1 atomic mass unit, each neutron weighs 1 atomic mass unit. This particular atom weighs 16 atomic mass units, which is AMU. But if we look here, it says actually the average atomic mass of oxygen is 15.999. And what that means is, yes, most have 8 neutrons, 8 protons, giving us 16 total. But some of them have 7. And that would make this 15. So if we average them out, a whole bunch of 16s with just a couple 15s is going to bring the average down from 16 just a smidge. And since this is so close to 16 here, we can say basically every oxygen you're going to interact with has 16, but there are a couple that have 7 neutrons, giving it 15, and that's going to bring that number down from 16 to 15.999. And this is called an isotope. Now it's super important for high school chemistry. It comes into play, later on in your chemistry knowledge, but you should be aware of it. An isotope is merely when it has kind of the non-standard number of neutrons. So let's get back to the standard number of neutrons. Let's get back to this model with 8 neutrons and 16 atomic mass units. Okay, there's the classic oxygen. Looking good, kid. Now, I'm going to make a little space. And I'm going to start, so I'm going to move this, though we remember that the 8 has to do with the protons. I'm going to move this up and into the corner. Just kind of leave it there for reference. And now we're going to start drawing electrons. Now, if I were going to draw this to scale, if the atom is this big, right? If the nucleus of the atom is this big, then the actual electrons would, how big I should draw where they go is actually kind of, as big as like San Mateo County. So I'm not going to draw it to scale. This is huge, and electrons wouldn't be anywhere near, on this board if I drew the nucleus this big. As they say, if you take kind of the average stadium for sports, like football stadium, baseball stadium, that sort of thing, and you take a quarter and you put a quarter down in the middle of the field, the quarter would be the nucleus, and the stands, the nosebleed section stands where I sit when I go see sports, that's where the closest electrons would be, just to give you a scale. But I'm not going to do that because I don't have the capability of drawing that big. So we're going to lie a little bit here, and we're going to draw some orbitals. Now we'll draw these first two. These guys are called orbitals. And orbitals are simply paths that you can take. I like to think of it as like car races. Like the orbitals are the path that the cars can race on. They're not going to drive through the middle of the field that's in the middle. They're not going to go out onto the highway. They're just going to stay on their track. And you should know that it's three-dimensional, which means not only can they go around and they go crazy, so they don't really go in a nice standard path or pattern, but they can also go towards the camera. They could go underneath. This would be a three-dimensional sphere, like a basketball, and they would travel around the basketball. And that's how it works. And they can go absolutely anywhere. I like to think of it as, take any kind of 4-year-old, 5-year-old, give them about 10 Red Bulls and let them go. And there, there they go. If you like tether them to the center and just tell them to run, that's exactly what an electron would be like. So electrons are zipping around like crazy. And these orbitals they come in 4 different flavors, and each flavor is a shape of the path that they can take. So these classic spherical ones are called s orbitals. So here is S1, and here is S2. Okay, and then there'd be an S3, S4, S5, out it goes. I don't want to spend a ton of time on orbitals, but you should know that S is kind of what everyone draws because that's the easiest one, but they also come in different flavors. And the other one I want to draw is the p orbitals. And there's a reason I'm going to draw S and p orbitals, and that comes into play in about 3 minutes. So the s orbitals are just classic spheres, with the innermost being S1 and then S2, and then there'd be one out here, S3, and then out there, S4, all that good stuff. Now the p orbitals. The p orbitals are like 2 teardrops. So their actual shape is kind of like that. And that would be considered one p orbital. And another p orbital would be that. And that would be considered another p orbital. So even though there's 4 kind of teardrop shapes, there's only 2 p orbitals. Now, this is called px because it would go along the x-axis of a graph. If this were a graph, this is called py because this would go along the y-axis of a graph. And then there'd be one that would stick up, and there'd be one that would go behind the board, and that would be called pz. And so there's only 3 p orbitals, even though they come in 6 different lobes. So these two are px, these two are py, and the one that kind of sticks up and the one that sticks behind, those two make up a pz orbital. Now, on each orbital shape, you can have up to 2 electrons. So for px can have 2 electrons, py can have 2 electrons, pz can have 2 electrons, which means total on the p orbitals is 6 electrons. Helps if you draw on camera there, Chief. Oh, really? Huh. I gotta write that down. That seems important. Where the S, well, there's only one shape. They don't have all these funky shapes. So each S can only hold 2 electrons. Now, there are technically 4. There's S, classic spheres. There's P, your teardrop shapes. There's D, and there's F. D, crazy, F, all kinds of bugaboo. Not going to draw them. But the reason that I bring this up is because these orbitals, these spherical s orbitals, these teardrop p orbitals, and just to put them all together, so the p orbital would kind of go like that. It would lay right over this. So let's get these guys out of the way. This is the px1 orbital, and this is, I'll do it up here. This is the py1 orbital. So both of these are px1, or sorry, not 1. Come on, Jay. 2. I have those kind of smarts. This is the px2 orbital. These are the py2 orbitals. And then there'd be a pz, both front and back, pz2 orbital. And just like s orbitals, where there'd be a s3 orbital that goes all the way around, there'd be a larger px3 orbital. And these things nest, like nesting dolls. So px2 is inside px3. py2 is inside py3. And as you can guess, this gets super noisy and hectic and terrible super fast. So most chemistry teachers just spend their time being like, they go in circles, let's just move on. And I'm going to do that for the rest of these videos, but this is what's really going on. And then you have d orbitals that are also jammed in here. And then you have f orbitals that are jammed in here. It gets so noisy. To give us this. So the periodic table of elements, that's kind of the last bit that we have to do today. The periodic table of elements is, the first thing we note is it looks nuts. It doesn't make sense. Why is there a gap here? Why not just make it a nice little rectangle, right? Why do you have these kind of stair step, moments? And what's this? Why is that down there? Why don't we just take this and just jam it right there, and we could fill out the rectangle? It'd be beautiful. And the answer is because the periodic table of elements is actually organized by how atoms act, depending on what orbitals, what paths their outermost electrons take. So the shape of the periodic table is actually based off of these different paths. If your outermost electrons are in a spherical path, an S path, then you'd be over here. These are the S path. Now they'll have other electrons, but if the outermost are S-shaped or spherical shaped, they'd be here. If your outermost ones are these teardrop ones, so there may be some inside ones, such as maybe you have px2, and px3. If px3 has your outermost electrons, the furthest electrons out, then you'd be over here. So this is your p spot. So all of these, their outermost electrons are in a p orbital. And then this spot here is all d orbitals. And then these guys down here are f orbitals. And I wouldn't feel like a complete teacher if I didn't show you the way the periodic table is actually supposed to be drawn. We don't draw it this way for the same reason why maps of the United States, we have Alaska and Hawaii just kind of flying in the ocean, just kind of cut out. That's what the f orbitals are. They are like Alaska and Hawaii. They totally belong to the periodic table, but we float them down here completely by themselves because putting them in is inconvenient. Now, if we were going to draw the periodic table correctly, what we would see is, and I'm gonna fudge just a little, and I know that, so you can complain in the comments on your own quietly. And that is, I would draw these first two s orbital guys, and technically this guy over here is also an s orbital guy. That guy right there, helium. So I would draw my s orbitals, and then I would drop down 2 rows and draw d. Oh wait, actually f sneaks in there. So I actually drop down, so there's 7 rows, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I would actually draw these f orbitals down here next. So I draw those, and there's 14 of them. Wow, just a bunch of them. I'm not drawing them all. And then I would draw this guy. And hopefully you see instantly that, and we run out of room. You know, putting these last 2 rows where they go, which is right here, these 2 rows should be put right here, and all of this should be stretched over to make room for these, like that, with this block here actually being this stuff here. But then where do you put this in the... All of our periodic tables would be super, super wide. They'd be super annoying to deal with. So what we do is we take this block, this second block, so this area right here, we just take it and we jam it down at the bottom, and we take this area and we just kind of smoosh that up, boom, with the s orbitals to be here. And so we have s orbitals here, d orbitals, p orbitals. But the way it should be is s orbitals, f orbitals, then next to f orbitals should be d orbitals and p orbitals. Again, not super critical to know at the high school level, but helpful to know down the road. So I might as well just keep introducing it here. Okay, well, we are getting there. Oh, by the way, this tells you the orbitals. So oxygen has 2 in the 2s and 4 in the 2p orbital, and implied in here is that there's 2 in the 1s orbital. So you'll see stuff like this with s's and p's and d's and f's telling you where the electrons are. Again, I'm not going to spend a lot of time on that in this review, but if this were a full review, I'd have you doing orbital diagrams and you'd have to like do all that stuff. But I'm not going to make you. Okay, last thing I really want to talk about is the different types of atoms. As in, atoms come in different flavors. And what are those flavors? That's a good question. It's really just kind of 3 basic flavors. So if we look at these yellow ones right here, those are called, and I'm going to start in the middle, those are called metalloids. So those guys right there are metalloids. Man, I love that name. And that's all these yellow ones. You'll notice there's not many of them, right? Everything to the right of it, everything up here, I'm going to use a darker green for that. So all of this, including the pink stuff, all of this, those are called nonmetals. And then check this out. Everything that's purple, everything that's blue, all of your f orbitals, the orange, the red, that green right there, all of this, everything that is on this side of the yellow blocks, all of that are metals. So if I chopped up the periodic table and took each tile and threw it in a bag, and I just kind of pull one out, most likely I'm going to pull out a metal. There's more different types of metals than there are nonmetals, and then metalloids are just the in-between. So metalloids have some characteristics of nonmetals and some characteristics of metals. They're just on that barrier. They're on the fence. Now metals, classic, you already know a lot about metals. They are shiny, right? They conduct electricity. Right? And coming into play in the next video, they hold valence electrons loosely. Now, valence electrons are the electrons that are on the outermost energy level. What that means is, if we look at, let's say, sulfur. If we look at sulfur, we see that sulfur is way out here. Now, we know that it has, and if we squint and get real close, we'll see there's a number 16 above it. It has 16 protons. And if we squint, we can look at the atomic mass and figure out how many neutrons there are in the average one. But it also, if it has no charge, not only does it have 16 protons, it has 16 electrons, which is the same as 1 more electron than phosphorus, or 2 more electrons than silicon, or 3 more electrons than aluminum. And that's how the periodic table fills, is it fills across. So if an atom only has 1 electron, then its electrons can behave like hydrogen electrons. And if it has 2, it would behave like helium electrons. 3, lithium, 4, beryllium, 5, boron, 6, carbon, 7, nitrogen. As we add more and more electrons zipping around the outside, this is how they fill. They just fill across the periodic table, which is why it's organized like this. So silicon has 16, which means in the first s orbital, there are 2. In the second s orbital, there are 2. In the second p orbital, there are 1, 2, 3, 4, 5, 6. In the 3p orbital, there are 1, 2. In the 3s orbital, there are 2. In the 3p orbital, there are 1, 2, 3, 4. And what it means is sulfur is a nonmetal, and it's going to hold on to those 4. So that's every electron that is in this row. The electrons that are way on the inside, they don't get to play with others. The electrons that are on the second energy level, they don't get to play with others. The electrons on the outermost energy level do get to play with others. They're on the outside. It's like eating, a gobstopper or a jawbreaker. You have to eat the outside first. That's the first thing you interact with. If I hand you a red gobstopper, you sit there and go, okay, that's the red gobstopper. I don't know what the inner levels look like, but the red gobstopper is red. I know that. The outermost is red. And that's how this works. You only get to deal with the outside ones. Now, nonmetals hold their valence electrons tightly. And what that means is sulfur, being a nonmetal, is going to hold on to 1, 2, 3, 4, 5, 6, these 6 electrons that are on the outermost energy level. Those 6, it's going to hold on to big time. It will not let go of them. Metals, on the other hand, metals are, wrong color. Metals are hippies. They'll totally share their valence electrons. So if we take something like magnesium, Again, its electrons are out here on the third energy level. But this one right here, this one, yeah, you can take my valence electrons, man. It's cool. And that's going to come into play a lot in tomorrow's video. So these guys, all of these, their electrons on their outermost energy level, the electrons furthest from the nucleus, they're going to be really loose with. Non-metals are going to hold on to them tightly. Metalloids, could be either, because it shares some metal characteristics and some non-metal characteristics. And let's finish up non-metals. First thing is, are they shiny? No, they're primarily gases. Or they're brittle. As in, they break, they don't bend. Do they conduct electricity? Nope. No conduction. No conducting. They do not conduct electricity, which is why the electricity that is flowing into the power cord, into my phone right here, is not zapping me because I put a lot of oxygen and nitrogen between me and it. And the oxygen and nitrogen in the air don't let that electricity flowing into the bottom of my phone flow into my hand. So thank you, non-metals, for not conducting electricity. Now, the last thing I want to say before we call this a video is the periodic table. There's a ton of information. I haven't printed all of it out. They'll tell you things like electronegativity and the boiling point and melting points and all this stuff. I chose a pretty simple one on purpose. But each one of these, each block is a different atom that's going to act uniquely. You can't really swap between them easily. Now, there are some that are close enough where you can swap, but a lot of them are actually pretty unique. And even though most of the types of the periodic table are metals, so all of these are metals, even though that's true, the most number of atoms are actually hydrogen. And here's the weird thing, even though it's over here, it's not a metal because is hydrogen shiny? No. Does it conduct electricity? No. Does it hold valence electrons loosely? You'll find out no. So it actually should be parked right here. And it should be a non-metal. So we should take this and we should just kind of pick it up and put it down right there. There's a reason we don't. I don't want to get into it right now. But for every, as I like to say, for every classification, there's always a platypus. There's always something that's not going to fit nice. For the metals, metalloids, non-metals, that right there